Okay, so hello, Dr. Ling, and everyone in the DSA course. Today, we are Group 11. We would like to present you about our group project demonstration of assignment 2, which we name it Exploring the Hamiltonian Path Problem on an Atomic Grid. So, moving on to the first part of the presentation slide, we will have 6 main points, including project team, project overview, data structures, algorithms, demonstration, benchmark, and last but not least, is further improvement. So, now we will be moving on to the first one. Our team consists of 4 members, including Hook, Sung, Yui, and me, management. So for each stay only once. So the timer starts at 0, 0, 0, and end at 7, 0. So the movement directions are provided in 63 character input string, consisting of D for down, U for up, L for left, and R for right, and stars as a wildcard for any directions. So our goal is to calculate the total number of valid paths that follow these constraints and measure the execution time in milliseconds. So this requires efficient exploration and optimizations to handle all the possibilities. So to solve the problem efficiently, we will use a dedicated method for exploring all possible paths, keeping the logic focused and streamlined. Optimization is key, as atomic grid involves more than 8 million possible paths, so we have to minimize the execution time by pruning invalid paths early and optimizing the search process. And also, testing will be ensure the solution works with random inputs and can handle edge cases, like timeout, without compromising accuracy. But in order to give you some context about our problem, so I would like to talk to you about our very general techniques to apply to our problem. So first of all is about the pathfinding. So what is pathfinding? So pathfinding is a fundamental computer science concept focusing on navigating networks of graphs to achieve goals while meeting constraints, such as avoiding obstacles or finding the shortest routes. It is widely applied in robotics for navigations, AI for decision making, gaming for puzzle optimizing resource functions, and an efficient pathfinding is essential for solving both theoretical and practical problems across various domains. Like for instance, like self-driving cars need pathfinding to avoid traffic jam, avoid accidents, or to find the shortest route without consuming too much time of the driver. Also, I would like to talk to you about the 2D grids as our graph. So a 2D grid is a simple but very effective structure for representing spatial layouts, consisting of rows and columns where each cell connects to each adjacent neighbor, allowing movement in 4 directions up, down, left, and right. So the structure is frequently used to model scenarios like maze, maps, and terrains, making it a practical choice for solving spatial problems like this. So by treating the grids as a graph, so cells act as points, vertices, and connections as are edges. So pathfinding algorithms can systematically explore and identify the optimal routes. So this approach can be found widely in robotics, like for help model navigation space, in video games like for designing character movements and levels, also in puzzles that require logical explorations. Moving on to depth search, backtracking, and narrative optimizations, I would like to leave the stage to Fook to handle all the definitions as well as the use case of these. So this is my part.
Hello, my name is Fook, and now I will be representing the algorithm part of our program. So the first part of our algorithm is that we implement a brute force approach with each the depth search and backtracking method. So for this method, we will start by exploring on part recursively and eliminating any invalid path early, which will reduce some unnecessary calculation. This is already suitable for our case where we want to find only the possible Hamiltonian path in the 2D grid, and really good for pruning any path that make the Hamiltonian path invalid. However, there are some limitations to this, which is that it's really inefficient for a larger site as well as really very expensive. Next, we also have some optimization, we call it the deduction method. This also makes some part more easy to prune and will making our Hamiltonian path by itself easier. So what do I mean by that? First, we divide the edges to the neighbor into 3 types. The first is that the required edges, delete edges, and then we finally have the undecided edges. But however, I will be only diving into required delete edges. First, how do we divide these edges? Whenever we travel to a neighbor cell, we will conduct a search and check for every neighbor around us. For example, the N1 and N2 and N3 on the graph here. And for every neighbor here, we will start by checking for the find adjacency node to see if that neighbor is required or delete edges. For example, for N1, we check for the cells C1, C2, C3, C4, C5, and the same goes for N2, which is C5, 6, 7, 8, 9. So, how do we define a required edges? Our required edges is that whenever a neighbor cell has 2 of the 3 adjacent blocks, A, B, C, visited, we will mark this cell as a required edges. Why? Because if we traverse to another cell, apart from this end, it will make a Hamiltonian path impossible because the cell block here will be a dead end and we cannot traverse to the destination point without reaching a dead end here or traverse to the block end here. Next, we have delete edges. So what are delete edges? Delete edges is that for our case where it's a little bit special, but whenever our node hit an obstacle, say it's body and you visited node on the edge, right, it will partition the grid into two different regions. Let's look at the example case 1, case 2, case 3 here. Whenever we travel to the block A, it will partition the grid into a different region, there's region C and region B. And whenever there's alteration on the grid, it makes it impossible to traverse on the block because it can only go to either C or B. So whenever either of the case is true, we mark this neighbor cell as the lead edge and we will not traverse to this. And the search will conduct the same for the N1 and N3. So that's the end of the algorithm part, and I will leave the demo demonstration part for you.
So I will get direct into our abstract data type. The first one is the array stock, which is the implementation of stock by using array. Just have some variable like size, the default max size, and then some item inside it. And the first one is the constructor, which create a new array stock with a given capacity, and the second one is the default constructor. It will create the array stock with the size 10, and then it's the array stock with this is the constructor with an array stock. Create an array stock with another array, and this function size going to get the size of the array stock, and the push function will push the new item on the top of the array stock and return the boolean true or false. And the next one is the array list iterator is served for the for loop in the Java with the array stock. And then I will move into the optional class. The optional class is this one will implement like the class is wrapped by the optional, need to be checked whether it have a data or not, and then the user cannot pass through it when it's wrapped by the optional. And then I have the 2D vector class implementation with the x and y value. It have some fixed direction, which means the 0 will return 0 0 and right, top, left, bottom, and some optional moving like top left, top right, bottom right, and bottom left. The return tree of this is the constructor for a vector, and then it have boolean to compare to vector. The self add it will multiple itself and add another vector and return into itself. Asymmetric subtract, and the next one is add to vector and return new vector. Also same for subtract and multiplication, and rotate left, rotate right is rotate the vector 90 degrees from to the left and to the right, and the flip is the vector 180 degrees. And I will go to the AF class, which have some text UI and mainly used for calling the function from read, and the read one is our main class. We have a constructor to create the grid with a fixed size with the star and the end position. The star is on the top left and the end is the bottom left. The read, the file on path is used to find on Hamiltonian path in the grid and mainly called by user. And the file on path helper, this can help the main function of our program is recursive call file neighbor to find on the valid path and return it. The find neighbor function is check and find which neighbor can be traveled through the current position. This will get the current pointer, and the step is the current step in the current position, and the optional direction then is to return a list of neighbor where it can travel through. So now I will move into demonstration the program. So I will press enter to start the program now. Then I will enter the grid size is 8. Then now I don't give any instruction, so press enter. This will executing the program. So wait a little bit. So then this will get the output is total path, and the execution time is 7.6. Then I enter to continue, and then now I will give an instruction for that. Now it will provide the total path is 5,739 with the execution time of 163 milliseconds. The same as the total path is the same as this one. So thank you for listening.
Hello everyone, my name is Sung, and now I will briefly walk you through the benchmarking process we implemented for evaluating our algorithm's performance across different grid sizes. To start off, we built a dedicated benchmarking class to systematically measure the key metrics of the algorithm. These metrics include the initialization time, how long does it take to pass the instruction into the grid, the total pass calculated, the calculation time, and as well as the memory usage. So the benchmarking process was designed to test various grid sizes systematically. By iterating over combinations of grid dimensions, we capture performance data that reflects real-world usage for these scenarios. So once collected, this data was written into a CSV file, and this format allows easy storage and ensure compatibility for further analysis and visualization. And finally, we visualize the results in Jupyter Notebook using heat maps and as well as other plots to identify the trends, such as how performance scale with grid size and complexity.
So this gave us a clear picture of the algorithm's strength as well as the bottlenecks. But however, for the moment, our benchmarking only covers one iteration. So therefore, we only cover all wildcard instructions for now. Since benchmarking random instructions would need a bigger data pool for accurate testing. And by automating and standardizing this process, we can confidently track improvements and ensure the algorithm performs optimally across all tested scenarios. So here are our heat maps and bar charts. So first, we have the total pass heat map and average calculation time heat map. The x-axis and y-axis represent the dimension of the grid, and we can see a clear trend here that the bigger the grid, the more complex and the longer it takes to run. As well as the memory usage heat map over here. However, there is a different trend here since the largest 8x8 takes lower memory than 8x5, for example. So this is probably due to Java garbage collection as well as how it handles its memory in our hypothesis. And finally, we have a bar chart for the total pass for each dimension pair, and it is represented on a logarithmic scale. So we can see how the grid dimensions affect the total pass. So thank you.